The entire semiconductor industry is focused on building a revolutionary transistor that doesn't exist yet. This is the story of the next transistor and the vertical leap required to build it. Moore's law, the engine of technological progress, promised a predictable doubling of transistor density every 2 years. That engine is now running out of fuel as we face diminishing returns and higher costs. We have pushed 2D transistor design to its physical limits. Even the latest gate-all-around, or GAA, transistors are still placed side by side, which does not solve the 2D packing problem on the chip surface. In late 2023, the big three chip makers, TSMC, Intel, and Samsung, aligned on a shared experimental design, the Complementary Field Effect Transistor, or CFET. This signals a consensus on the future of the transistor. The CFET blueprint involves folding the standard complementary pair of transistors. Instead of placing them side by side, the NFET and PFET are stacked vertically, cutting the footprint in half. This shift from horizontal to vertical scaling is like turning a single-story house into a 2-story duplex. The primary win is density, effectively halving the footprint of a logic gate and keeping Moore's law alive. While the CFET concept is elegant, manufacturing a 2-story transistor at an atomic scale presents 5 monumental hurdles: integration, alignment, fabrication, heat, and the design ecosystem. Challenge 1 is the integration scheme. We must choose between monolithic integration, a continuous process requiring extreme control, or sequential integration, which offers material optimization but introduces thermal and alignment risks. Challenge 2 is atomic scale alignment. Stacking billions of transistors requires aligning patterns across layers with less than 10 nanometers of tolerance. A tiny misalignment can lead to massive defects. Challenge 3 is process complexity. The tall CFET structure makes etching, deposition, and isolation far more difficult than with a single flat transistor. For example, deep trenches must be filled without creating voids. Challenge 4 is trapped heat. The bottom transistor is buried, making it harder to shed heat. The solution may be using metal rails from an innovative backside power delivery system to act as heat conduits. Challenge 5 is redesigning the entire ecosystem. A 3D transistor requires adapting everything: the fundamental standard cells, the EDA tools that automate design, and the engineers who must manage new constraints like heat and noise coupling. Despite these challenges, progress is real. TSMC demonstrated an existence proof, achieving over 90% device survival rate on a small-scale CFET stack. The success of the CFET will determine the pace of technological innovation for the next decade.